Hello guys, so we're going to be talking, I'm Katie and I'm going to be discussing section 7. So we're going to talk about more Bayes nets and also decision nets. Okay, so for question 1, we have a question about inference. So we're given this Bayes net here, where we have two variables that are observed. So E and H, we know what values they have. The first question asks you, what is the number of rows in the largest factor generated by inference by enumeration? So when we're talking about inference by enumeration, we're usually talking about what is the size of the table that we are creating, or how many rows is it going to have if we have all the unobserved variables. So we're going to see that we have 1, 2, 3, 4, 5, 6 unobserved variables, 8 variables in total, but E and H are observed. So we're going to have 2 to the 6th number of rows because they are binary. Okay, so for question number 2, it's asking us if we have this Bayes net and we wanted to find the query P of B, D given E and H, how are we going to, what would be the variable elimination method that would be the variables that we eliminate that would be the most optimal? And by optimal, we mean the size of the factors are the smallest. So most space saving, you can think of it. So I'm not going to go over all of them, but in general, if we have a Bayes net, a heuristic that you can use to see which one would be most optimal would be which variables will we eliminate that causes the least disturbance in the rest of the Bayes net. So just looking at it like this, we can see that C would probably not be one that we would eliminate early on because it has a lot of variables that depend on it, such as A, B, E, and F. So just looking at it roughly, we would probably think we want to eliminate either G or F first. So because I know the correct answer, I'm not going to directly go for the one that is the most optimal, which I will just tell you right now. It's going to be this one. I'm going to instead look at this variable elimination. So this is F, G, C, and A, and I'm going to show that it is less optimal than the true optimal. So just starting off, let's see what would happen if we try to eliminate variable F. So eliminating variable F, we are going to create a factor where we sum up over all the values of F, and we're going to create the values, we're going to take the probability of F given C multiplied by the probability of G given F. And then we're going to sum over all the possible F's. This is going to give us a factor that contains G and C. So looking at it, we see that there are 2 unobserved variables. So the first factor elimination is going to give us 2 squared, a table that has size 2 squared. Similarly, looking at G, once we have F observed, F eliminated, we're going to cross that one off. You can think of that one as being crossed off. And then G all of a sudden would have nothing really, and then we can just eliminate that. G itself takes on 2 variables. 2 values because it is binary, so G has 1. Okay, so the next value that we want to eliminate is C. Creating a factor, we're going to get summing over all the values of C. We're going to have a factor which now does not contain G because G is also eliminated. Just cross it out because that one's gone as well. We're going to have the factors that P of C given A. We're also going to have P of E equals the thing we have given B and C. So this is going to give us a factor that contains A, E equals E, and B. So this one has, looking at it, we see that this has 2 unobserved variables. So this one is going to give us a factor of that size. So now that we have C eliminated, now we just look at A. That's going to give us, well, just looking at it, we see that it's going to depend on 2 values, B and D. So even without having to generate the factor, we can see that this one has this size. So now that we know this one, let's see how big, if we had eliminated it in this order, how big the factor table that we have to have would be. So let me just erase what we had here. So first we're going to now try to eliminate G. Eliminating G, we're going to have sum over G of all the things that depend on G. So we're going to have P of H given G. So H, this one is given. So we already have H is equal to H. Given G, P of G given E is also given. So we have this one. And F. So this is looking at the base net. So the factor that we create from this is going to consist of H, but H is given. E, but E is also given. And lastly, F. So these two are givens. So this factor that actually gets generated only has one observed variable, so this is going to be 2 to the first. So that's going to be size that we create from there. Now G is eliminated. Now if we were to eliminate F next, similarly we would look at it, and we can see from here that only C is going to be the unobserved variable, but we can real quick generate the factor just to be a little more rigorous. So let's create this factor, sum over all the values of F, and then we have this new factor that is created. We have F given C. So looking at it, there's nothing else. We can create this factor that now contains H, E, C, except for these two are also given. So the only unobserved variable we have is indeed C, so this one's also 2 to the first power. Similarly with C, now that we have eliminated here, we can just, using a similar method, now that we have a more I for it, we can see that to eliminate C, the variables that depend on it are 2 of them. It would be A and B. A and B, if we have 2 unobserved variables that depend on C, we're going to have a factor of this size. Similarly, when we remove that one, we only have A left. A remaining, we already saw from previously, it's going to have a size of 2, so we're going to have this. So we can see that these two are pretty close, but then this one beats it out by a little more simply because we chose to eliminate G first, which gets rid of some of the variables. Okay, so now we're going to look at the next question. We want to find 2 things. One is when F is eliminated, what is the intermediate factor generated, and how to calculate it. And then the second part, we want to see what would be the minimal new base net that we can draw to represent this distribution. So looking at this one, it's always easier to solve for the right-hand side first and then create the factor. So let's scroll back up to this base net. Let me get rid of the markings from previous. So we see this base net. We want to see the ones that are that affect F. So we have G given F, and G given F and E, and we also have F given C. So let's just write that down. So we want to write that this one is going to depend on the probability of this F given C, as we saw from above. And then we also have the second one, which is the probability of G given F and E. And then the next step is just to sum over it, which they give for us. So we're done with the right-hand side. So the left-hand side, they want us to tell them, they want us to create a factor that is generated by this summation. So we can simply just write out all the variables that depend on it, that are not F, which do not get eliminated. And then those are going to be G, C, and E, which E is observed. So the reason why we put G on the left-hand side is because it appears on the left here, and then C appears on the right. So that is a general rule you can think of. Now, how do we represent this new factor in our base net? So keep in mind, all of a sudden, we don't have F, which is shown here. There is no F here. But we still somehow need to represent that the G, given C and E, is a probability distribution that we have. So how can we show that? There's many ways. We can create a fake variable and then call this f prime and then have them pointing that. That's obviously going to work, but that's not going to be the most optimal. So very intuitively, we can draw an edge from C to E, and that would give us the distribution that we want. Okay, so the next question that we're going to talk about is a sampling question. So we're going to cover a few sampling techniques in this example. So let's start off with question 1. So they want us to use these samples that they gave us here to calculate the estimated probability of W2 equals R. So very simply, we are going to have that the estimated probability, put a hat to mention that it is estimated. This one is going to equal to the number of samples that contain W2 equals R. And then we're going to divide that by the total number of samples. So the reason why this works is assuming we have just a bunch of samples, and then we, to get the unbiased estimate of W2 equals R, we're going to see that it's going to fall under this distribution. So let's look at all the things that have W2 equal to R. We see that there is 1, 2, 3, 4, and 5 of them. There's a total of 10 of them, so we have 5 over 10. This gives us an estimated 0.5 probability. Now going on to question 2, they want us to cross out all samples which are rejected by rejection sampling, and then our evidence variables are these two, I1 equals T and I2 equals F. So very simply, we're just going to look at all the samples that are above that do not have I1 equals T and I2 equals F. So this actually eliminates most of them. So these don't have it. These also don't have it. These don't have it. These don't have it. In fact, this one has it, this one has it, and nothing else has it. So this actually gets rid of a lot of our samples. So this doesn't help us too much. So instead, let's use a better sampling technique. So this one is going to be called likelihood weighting sampling. So we're going to generate, they give us that they generated these samples for us, which is very nice. So now we don't have to generate it ourselves, but we do need to calculate the weights of them. You can think of likelihood weighting sampling as the weights being we are hallucinating these samples. So if these samples are more likely to occur, we're going to pretend we saw a lot more of them. If they're less likely to occur, we're going to pretend we saw less of them. So just jumping right in. For question 3, it wants us to calculate the weight of the first sample, STRF. So we can just calculate it. Writing out the equation, we have the weight of the sample is equal to the product of all the evidence variables of the probability of getting that evidence variable given the parents of the evidence variable. So this is just the equation, nothing super special about it. We plug in the values. The evidence variables, looking here, we have evidence variables are I1 equals T and I2 equals F. Scrolling back up, we see that the parents of I1 is equal to W1, and then the parent of I2 is W2 respectively. So we're just going to write out the probabilities. So this is going to equal to the probability of I1 equaling true, given that its parent, W1, is equal to, they want us to set it equal to S. And then we multiply it similarly with the product of I2 equals T, given F, given W1 is equal to R. So now we can easily find out these values as well. Given the probability tables, scroll up. The ones that we are interested in are the values of I1 given S. So that's going to be here. I1 is going to be false, and this one, so this is 0.9, this value. And the second value we're interested is if it's false and it's rainy, so that's this value. Plug the values in. You get that this is equal to 0.9 times 0.8 is this is going to give us a final probability of 0.72. This is not a probability, but a weight of the sample. We're saying that it is quite likely to see the sample, so we're going to pretend we saw a lot of them. Okay, so the next part wants us to use likelihood weighting to estimate this value here. But to actually do it, we need to calculate the probability of all the samples. So real quick, let's just do it. It's going to be very similar to how we solved for this value here. So we have that the first sample is going to be 0.72, have probability of that. We said that that sample actually occurs twice, so we can remove some of the work that we need to do and say that that's the case. What about for the sample RTRF? So this one is going to be the probability of I1 equaling to true, given that W1 is equal to rainy. And then we're going to have the probability of I2 equals false, given that that day is also equal to raining. So plugging in the values in the above table, we're going to see that this one's 0.16, meaning this sample is actually not very likely. Similarly for these two, we're going to have that this is going to be 0.09. Since it's the same, this one's going to be the same thing. I'm just saying that this is very unlikely. And then for the last one, plugging in the values for given in the table above, we're going to get 0.02 as well. So now that we have the weights of all the samples, we would solve it normally. We're going to have the probability of, well, since we want an unobserved W2, we have to do both of them. So let's do W2 equals rainy first, and then we can solve for the second one, probability of W2 equals sunny. Given these, this one's I1 equals to true, I2 is false. This is going to equal to the number of samples, but all of a sudden our samples aren't going to be sum of 1, divided by the total number of samples. I put quotes around this because all of a sudden it's not the true samples anymore, they're the weights of the sample. So we're going to sum over the weights of the samples with W2 equals R, I1 equals true, I2 equals false. I'm going to divide by the total number of weights. Looking at the samples that we have over there, the ones that contain this distribution is going to give us this one has it, this one has it, and then lastly we have that this one has it. So we're going to sum over 0.72 plus 0.16 plus 0.72 divided by the total number. Forgetting a 0.72. Okay, so this solving for this one requires some basic arithmetic, but you're going to end up with 0.889. Similarly for this one, if we were to solve, we can calculate it mathematically using the same way, but we can actually rely on a trick because we know that the only two possibilities for these are raining and sunny. So they have to sum up to 1. So we can simply just do 1 minus what we got previously. That's going to be our second probability. Okay, so the last question that is in this week's discussion worksheet is a decision network and VPI question. Decision network and VPI usually consists of a decision network where we have things that are similar to what we saw before, which is T depends on Q. And then this utility node. This utility node is slightly different from like a actual outcome, but this is going to also depend on stuff. So there's an action, which is, in our case, we want to buy a car or not buy a car, or Q, which is the quality. So it's going to depend on those two values. So, jumping into this question, number 1, they want us to calculate the expected net gain from buying car C given no test. So we are not given any additional information. So we can see that the base net for this one, or the decision net, I should use the correct term, is simply going to be or we're not given any additional information. So let's just jump into it. If we want to calculate this, I'm going to denote that the expected utility of this action buy, this is going to equal to, just like regular expected utility, we're going to take the probability of something occurring, which is going to be Q, the probability that the quality is good, multiplied by the utility of it being good. And since we're only given one action, it's going to be buy. And then we're going to add it to the other one, the probability that is not good, times the utility that is not good, such that we buy it. So there's only these two. This is as you would normally calculate an expected utility. Plugging in the values that we have, we see that there's a 70% chance that it is good, and then if you have a good car, you're able to sell it, or it takes you this much, 1,500 to buy it, and it has a market value of 2,000, so it's pretty good. You end up earning $500. So let's just write that down. But what if it isn't good? We have a 30% chance that that's going to happen. And if it isn't good, you're going to have to spend $700 in repair. The car is still going to be the same price, and its market value is only that much, so you're going to end up losing $200. So this is going to be our equation. Doing a bit of arithmetic, we see that this gives you 290. So the expected value, if you choose to buy this car, or expected utility, is going to be $290 if you choose the action buy. As a thought experiment, if we choose the action of not buying, we're going to have 0. We're not going to it's not going to cost us anything to buy it because we're not even buying it. And that's going to give us a expected utility of 0. Okay, now we're going to look at the idea where all of a sudden we are allowed to make tests. So let's see. They tell us that the probability of a test passing given the quality is going to be these two values. And now they want us to calculate the probability that it is in good or bad shape given each possible test outcome. So the possible test outcomes that we have to take into consideration are it passing or failing, and then we want to calculate the probability that the test passes or the probability that the test fails. So let's just start by calculating for the probability that the tests pass. This value is going to be sum over all the possible qualities of a test passing and the quality, car being a certain quality. Not multiply. This itself is going to be equal to the sum over all the qualities of test passing given the test itself multiplied by the probability of the quality. So this second equation we get from BaseNet, we see that there's only two possibilities of it being a certain way. So we can just plug in the values. So we get 0.9 times the probability that it is good quality is 0.3. And then we add it to the probability that the quality is bad, so that has 0.2 probability of passing if the quality is bad, and the quality is bad 0.3 times. Oh, let me change this. This is 0.7 from above. So this is going to give us 0.69. So that's going to give us our final probability, which is 0.69. What about the probability that the test fails? Similarly, we're going to use the same equation up there, but this time I'm not going to write it out because that's a little redundant. Let's just write over all the possible qualities, the probability that the test equals fails, given the quality, multiplied by the probability of it being a certain quality. So that's going to be a certain value, but we don't actually need to calculate this because we know that the only two possibilities are if it passes or if it fails. Since we already calculated one value, we can rely on our trick again. We subtract it. This is going to give us 0.22. Or approximately 0.22. 0.31. Okay, so now that we have these two, we can go on to calculate the probability that it is good or bad given the possible test outcome. So let's first check to see if it is good quality given that it passes the test. We probably don't need it. We can calculate the other one, but we're just not going to check the quality is bad given each of the tests because that one we can use the same trick and do one subtracting from it. So let's just start off with the probability that the quality is good given that it passes. So this one, we can use Bayes' rule. So this is equal to the probability that the test passes given that the quality is good, multiplied by the probability that the quality is good, divided by the probability that the test passes. So we're going to see that we actually have all these values, which is very nice for us. We can just plug the values in. We get 0.9, which is from above, multiplied by 0.7, which is the probability that the quality is good, divided by the value that we saw here, which is 0.69. So this is approximately equal to 0.91. So we can see that if the test passes, we have a very high chance that the quality is also good. Let's see if the test passes, if the test fails, what is the probability that it is good? So let's calculate that. So this is a false negative. Let's calculate the false negatives. So once again, plugging into the Bayes' rule, using Bayes' rule, we have test equals fail, given that the quality is actually good. I'm going to divide this by the probability that the test fails. So, plugging in the values again, we get that this is going to be 0.1. Oh, this one's 0.1 times 0.7 divided by 0.31, which we calculated above. This is going to be approximately 0.22. So we have a false negative of about, we have a 22% chance of a false negative. Okay, so the next question wants us to calculate the optimal decisions if we see a passing test or a failing test. And then the way we can calculate it is by using expected utility, so we might as well calculate them as well. So let's see. If we want to have, let's first start with if we choose the action by, because that's going to be the one that gives us the most unique values. If we want to see the expected utility of a buying action, given that we saw a test pass. Let's just start with that. So let's just calculate it. Is equal to the probability that the quality is good given that we saw the test passed, multiplied by the utility of the quality is good, and we bought it. And then the only other option is the probability that the quality isn't good, given that we passed the test, multiplied by the utility as well. Oh, this is negative. Not good. So this is going to be plugging in the values that we calculated above. We're going to get 0.91 multiplied by, if we bought it, this is 500 gain. Similarly for this one, we're going to have that the probability that it is not good, given that it passed the test, is just 1 minus that value. So that's going to be 0.09 multiplied by negative 200, which is if we bought it and it was bad quality. So that's going to give us approximately 437. So if we had gotten this test result and it showed that it passed, and we chose the action buy, we would see an expected utility of this amount. But what if we choose the action buy given the pass failed? Let's calculate for it. So this is plugging into a similar equation. We're going to get that. We're going to get that these distributions change. The utilities don't change, but the probabilities of each of the respective ones are going to change. So we calculated this above. What is the probability of the good quality? We saw this one. It's going to be 0.22 multiplied by 500 again, because of the same utility. And then the probability that it is bad, given that it failed the test, is just going to be 1 minus that. So we're going to have 0.78 multiplied by negative 200. This is going to give us approximately negative 46. Expected utility. So if we see that the test failed and we bought it anyways, we would expect to lose $46. Now what if we just choose to not buy? So let's see the expected utility of not buying given test fails. That's going to equal to 0 because we're not spending money, we're not doing anything. But that's also going to be equal to the expected utility of if we didn't buy. And we saw good things from the test, which is that it passed. So we see that all of these equal to 0 if we choose the action to not buy. So just looking at this, we can see that if we saw that the test passed, we probably should buy it because the maximum of them is this one. And if we saw that the test failed, our better option would just be to not do anything rather than lose $46. Okay, so for the last part, they want us to calculate the value of perfect information of the test. Should the buyer pay for the test? So we'll just see if it's worth it for the buyer then. Just as a reminder, it takes them $50 to pay for the test, which we see over here. The test costs $50. So we want to see if it's better than that. So let's just calculate it. The equation for the value of perfect information, given the test, so we want to know what happens if we see the test, it's going to be the product, the sum of all the results of the test multiplied by the probability of the test showing a certain result, multiplied by the maximum expected utility, which we calculated above here, of that test showing that result. And this whole thing, we're going to subtract from it the maximum expected utility of if we didn't know anything, which is what we calculated in the first part. So this is just going to equal to what we saw before, this value, 290. So we can just write this in just to remind ourselves. This is 290. We want to see if this part is a lot better than that one. So the two possible values, the two possible outcomes of this test are either it passes or it fails. So the probability that it passes the test or the probability that it fails the test was also calculated over here. So we have these two values. So the probability that it passes is 0.69. We're going to multiply it by the maximum expected utility, which is here, 437. The second result is that it fails. The probability of it failing is 0.31. We're going to multiply that by the maximum expected utility, which is 0. And then we're going to subtract from it by the maximum expected utility of nothing, no information, which is going to be 290. Doing some arithmetic, we're going to see that this is approximately 11.53. So by knowing this information, we are approximately gaining $11.53 of value. So we check, is this greater than the $50 it costs us to buy it? It's not really. So should the buyer pay for the test? Probably not. But on a moral standpoint, you should still probably pay for the test. But by the calculation, the buyer should not. Pay for the test. Because it is not worth it.